Hey, happy Sunday. This is PFG Live, the podcast that is the standard for randomness. Welcome aboard. We got a bunch of guys in Discord today and a few on the YouTubes. Let's see. The first guy checking in was CJ Stevens, who reported 94 degrees and sunny in East Tennessee. A great day to be working inside. Josh is reporting the music is live, the audio is check, and from southern Manitoba, he reports winds are 260 at 8 knots, gusting 19 knots, temperature 21, dew point 19, and the remarks indicate some stuff going on. Dale from Widgetworks says it's 16 degrees science and cloudy in the Canada, where we get blamed for getting you to park at the correct airport and you still miss your flight. Sorry. Warren Jones says the same weather as you, my friend, and that is true. And right now here in the Windham, it is 71 degrees, 80% humidity, and we have had rain today. Tucker says it's sunny and 84 in the Buffalo, New York. So much nicer in the shade. New York Machinist from the Ithaca, New York, stay out of the gorge, says it's 80 degrees Fahrenheit and cloudy with plenty breezy. I know plenty breezy. Manchester Airport is currently reporting winds 9 knots, visibility 3 miles in mist. Broken at 800, overcast at 1600, temperature 21, dew point 18, altimeter 295 remarks. Surface visibility 5, rain ended 17 minutes after the hour. Awesome. Let's see, who are we missing here? Carl Tauber from the People's Republic of Rhode Island says it's 74 degrees and threatening rain in Rhode Island. Thank you, Carl. Art that makes art. Wes says it's warm in the Idaho. Welcome. Keep our favorite potatoes just the right temperature with the bacon and the butter. Ooh. Yeah. Well, welcome aboard, everyone. It's one of those mornings where if you could have just stayed in bed and that would have been a good choice, but the air conditioners have saved us in the last couple of weeks, and I am not apologizing for them. It's been pretty good. Shop stuff has been kind of fun. I'd like to hear what are you guys doing in the shop? I know Warren said that he was single point threading, working on his big machines. I was talking yesterday with DBX about his really cool handheld router CNC gizmo, which was very interesting. And on Discord, and this is sort of one of the things that triggered the thoughts for today. On Discord, I was talking to Mr. James Clow42, about step over and such on the grinder. He has the CNC grinder project going. And we talked about potentially, some features. We'll talk about it later, but I know he's been working on that project as well as others. So what else are you guys up to? Let's see. CJ Stevens just did a thing, which I saw in the chat, working on a projector protector for a golf simulator. And CJ Stevens is also powder coating Jeep parts and welding aluminum projector covers. Powder coating is something that I have not gotten into, but I'm happy to have people who do it not too far away. Quentin is with us. Welcome aboard, Quentin. He's reassembling the drill press after paint while listening. We need a weather report, dude. You are our representative this morning in the Netherlands. New York Machinist is doing a brake job on the Civic and machining a spindle housing, hiding from the heat. Yes. Well, I'm glad we got a little bit of a break anyway. You don't like powder coating? I think if I had a big dedicated space for it, it might be kind of fun, but I don't. So the place that I like to go for those sort of things, this is not not sponsored, I just like these guys, is Applied Graphics up the street in Amesbury. They've done some really nice work for me. and they do powder coating, amongst other things. So if I need something done, that's where I'll go. Okay, Quentin has given us a weather report from Echo Hotel Kilo Delta. Winds are 320 at 10 knots, 280 variable 360. No significant weather. Scattered at 2100, broken 2500, broken at 2900. Temperature 19, 2.13. Altimeter, I got to get this right. I think it's, how does it go? 10,000. It's 1014 millimeters of mercury. I think that's how it goes. No significant weather. Cool. So we were talking about this grinder project, and I made a comment that said, something that I think would be really neat. Oh, let me back up. Mr. Cloud42 said, I remember Solid Rock Machining saying something about, was it Solid Rock or was it Shark River? Now I have to go back in the chat, saying something about never grind over the same path twice. And of course, if you have a CNC grinder, one of the problems is it's too consistent. A CNC grinder will do exactly what you tell it to over and over and over again. And it's very, very consistent. Well, extreme consistency can lead to visible grinder lines on the work. So I said, what would be really cool would be a feature that gives it a band of values for step over on the surface grinder, and then add some randomness to it. In other words, it will step over not less than the minimum, not more than the maximum, but it'll be random in between those two values. I think that has some value to it, and we could talk a little bit about why that is so. One of the fallacies about grinding, and I know you've heard this before, is that when you dress the wheel, you actually get the bottom of the wheel very flat. And then as you use the wheel wears. So you end up with it being not flat. It becomes convex. And depending on how you approach things, you can control how convex it gets and how much that matters. But the fact of the matter is that your wheel is flat only the moment after you dressed it. So now if you're stepping over, which you are when you're surface grinding, if you're stepping over and you have that curve in the wheel and you step over a high value, then you're going to get that curve in your work. And that's not what you want. So typically when you want to get that nice flat area, you're going to reduce your step over by a large value so that you never see that curve, or it's the amount you're seeing of that curve is such a low value that it doesn't matter. And this is what, we chase this feature of, controlling the wheel wear when we do surface grinding. And if you imagine, a wheel that's flat on the bottom and then you start surface grinding with it, it's going to wear every time you step forward and step backward. It's going to wear on that edge, and you may still have a portion of the wheel which is still flat. And then as that wear approaches each other, and then the wear, intersects, you should have dressed already. You should have gone back and dressed, and that's how you control getting that nice surface finish. But there's that all makes sense if you assume that you're going to get the cut on the work is the shape of the wheel. What happens when there's other effects that happen? Like, for example, you're heating the work up, so the work actually grows and you're grinding off a little more in that position. Or what happens if you're grinding something, I don't know, like a stone, and you can push on particles and kind of push them out of the way because they're not very strong. They have friability. The work has friability. So that's an important question. And so randomizing how the wheel approaches the work can have some serious value. I was eating breakfast this morning, and I'm thinking about what other areas where this is appropriate. One of them, we just mentioned powder coating, right? Okay, so if you do a good job of powder coating and you look at your powder coat before you cure it, what should you see? What kind of pattern should you see in your powder coating? And the answer is you shouldn't see a pattern. So you want a very, very random approach to coating the thing. You don't want anything that leaves a pattern, because otherwise you're going to see the pattern in the work. I looked up at the ceiling while I was eating breakfast, and I noticed the kitchen has a popcorn ceiling. So a popcorn ceiling is when you have the drywall on the ceiling. Okay. They put the drywall up, and then they come in, they tape the seams, and they fill in the divots, and if you looked at a completely ready for finish ceiling in a well done room, you're still going to see things, right? And if you paint it, chances are, and I could probably see that in the room I'm in, if you paint it, chances are you'll see little places where there's a screw underneath, or little places where the two sheets of drywall meet. In fact, if you look right over my head here, let's see if I could point at it. See, it's a little darker right there, right? You can even see it in the camera. There's a little wave in the ceiling over there. Look at that. CJ's showing us some of his parts. Beautiful. I like the cabinet. So we come along and we spray it with this stuff, which is called popcorn. I don't know the details. It's probably a special gun, and we're left with these little random dots on the ceiling. And when it cures and you look up, it looks perfect. There's no pattern. You can't see a pattern because all those little dots are covering up the patterns that were there. That's randomness. Okay. And as long as the operator did a good job, then it's going to look completely random. The same thing happens with if you pick up your grinding wheel and you look at the grinding wheel, at the bottom of the grinding wheel, it looks random. All the particles look very random. And ultimately, if you're trying to get a perfect finish, okay, the particles on top of the surface should be random. And so the randomness results in a smooth looking surface with no defects. Does it matter if it's a little bit non-random? No, but that's random. So how do you get that in a system such that when you're finished cutting or you're finished grinding, you're finished doing your job, everything looks smooth, and smooth is random. And the answer is you have to address the things that aren't random. And like we were talking about earlier, one of the things that aren't random is doing the same exact step over every time. So you break that up. Another insidious place is chatter. So if you're working on tell me if this has happened to you working on a lathe. You're working on the lathe and you're doing a cut, and all of a sudden you start to get chatter, and maybe it starts singing and you could hear it, and when you finish that pass or you stop that pass and you look at it, you see waves on the surface from the tool chattering. And You don't want that. Did you ever? I liked because Adam Booth did a bunch of, obviously over the years has done a bunch of manual machining, and if he gets chatter, he stops immediately, and you'll hear him say these words. He says, "Okay, I'm going to do a deeper cut and get under the chatter," and he might slow it down. We'll talk about that and do some other things. And the reason is that if you get chatter and then you just say, well, it'll come out on the next pass, what happens is the wear on the pattern on the work is going to excite the same resonance that existed that caused the chatter in the first place, which brings up this new term called resonance. So resonance is that property that causes something to vibrate at a frequency, a very specific preferred frequency. And in your system, if you're getting chatter, then something wants to chatter, and it could be a resonance in the system. It could be a resonance at a particular speed for a particular cut when the chip is being let go is just the right frequency that it's going to come back. Art that makes art. Are you sure it's not harmonics? So let's talk about the word harmonics. That's a good point. So harmonics, the definition of harmonics is integer multiples of a frequency. So you could have a frequency, let's say a kilohertz, okay? And the second harmonic of a kilohertz is 2 kilohertz. And the third harmonic of a kilohertz is 3 kilohertz, etc. So if you have a resonance in the system, you could excite that resonance with one of its harmonics, okay? And they're all related. So that's where harmonics come from. Harmonics are multiples of some resonance. So in lathe work, what do? We slow the work down because at the lower frequency of turning the work and the diving board, which is the tool with the cutting edge on it, if we slow the work down, we're tending to not excite that high frequency. In lathes, I know Haas started doing this, and there was a name for this feature, and I don't remember it. But in lathes, you can vary. Thank you very much. Oh, Josh was reading my mind. SSV. Do we know what that means? Spindle speed variation. Thank you very much. So it'll continuously and probably not randomly, but it should be random, change the spindle speed so that if there is a resonance in that range, it's not going to dwell on that resonance. It's going to go past that frequency and not excite that chatter. And it's a great idea. Okay. One of the things that happens in surface grinders with hydraulic tables is, Josh says you set an upper and a lower RPM. Perfect. In surface grinders with hydraulic tables and the stupid little throttle is you're not going to set that table exactly the same every time. So that changes things up a little bit. And for a particular grind, if you start getting some weirdness, you could change the table speed a little bit, and it's not going to very significantly change the rest of your parameters, and you can get away from some resonance in the system. G96. See, I knew one of you guys would know that. So Wes says it's G96 in the Haas. I think it's a great idea. I think it's magnificent. So I know James will be listening to this later. The ability to have a little... Carl. Carl just named it spread spectrum machining. Carl, that's perfect. That's ideal. So Well, there's the name, James. Spread spectrum machining. You nailed it. You can randomly change that step over. You could randomly change other elements to stay away from the harmonics. Another place you get a harmonic is from an imbalance in a wheel. Okay, so you have a wheel that you're running on your surface grinder, and there's an imbalance in it. And you can model that imbalance as like a mass on the wheel that shouldn't be there. So as it goes around, it's going to wiggle the spindle up and down. Carl says you could also call it frequency agile. Yeah, that sounds a little bit like changing channels, but I like spread spectrum. That was the right one. That was perfect. So if you have a wheel that's bouncing around, right? How can you, let's say you have an imperfect grinding wheel, and they're all imperfect, right? Okay, Art corrects himself. Not Art. Wes corrects himself. He says it's M139 on the Haas. Thank you. Good job. So let's say you have an imbalance in your grinding wheel. Can you grind with that wheel, or should you throw it out? Well, of course, you should. You should balance your damn wheel. Go to pfg.gg/BAL. But you can still slow down and get away from the effect of that imbalance and make it through. That's a way to do it. That's a way to get away from that. So if you go fast, you could see the evidence. If you go slow, you start to not be able to see the evidence. So that's another, and it's the same thing in my mind. You're slowing something down to get away from a resonance. You're going lower in frequency to get away from the resonance. The same thing with your spindle speed on the lathe. Going back to the diving board, on a lathe, it's pretty obvious that you have a tool sitting out like a diving board, and it's got some sort of bend to it, right? Everything's rubber, and that could result in a resonance. A mass on a spring is a resonance. Well, in a grinding wheel, a grinding wheel is very stiff when you push on it on the face of the wheel, but when you push on the side of the wheel, something happens. It's called the wheel's going to bend. It's the weakest mode of the grinding wheel. So that when you side wheel, and we talked a little bit about side wheel. Yes, I'll address that, Wes. Thank you. When you side wheel on a surface grinder, you are much more susceptible to having the wheel ring and leave a pattern on the work. You can take the same wheel and just turn out absolutely perfect surfaces that look, perfectly random, very smooth, and then you go to side wheel with it and it looks terrible because it is ringing. So when we're taught in the world of grinding, but before you mount a wheel, you hold it up on a pencil and you tap it with a little hard thing, and you listen for the ring. Because if it rings, it's solid and it doesn't have a hidden crack. That's awesome. It also happens to demonstrate exactly what we're talking about. The side wheeling, the wheel has a resonance in that mode, okay? And we can excite that resonance. Tucker says side wheel is also much less supported than regular grinding. Yeah, we're violently saying the same thing. Well, actually, you might be talking about further up the kinematic chain, right? When we're pushing on a spindle one way, it's not the direction it was designed to be. But really, the wheel is bendy, and that's where you get the ringing from. Well, you can excite that ringing by side wheeling. Now, Wes brings up a really excellent point. He says you can also speed up. I'm going to change your words a little bit, Wes, forgive me. You could speed up to avoid a resonance. Okay. So let's say you're on the lathe, right? And you do have your cutting tool and your diving board, and you're starting to get chatter. The knee jerk reaction is to lower the spindle rate to get away from the resonance. Okay. Well, Wes says you could also speed up to get away from the resonance. So that's absolutely true. You just have to get away from the resonance. So think about that when you start to get these undesirable patterns in the work, and do use your ears. Your ears are going to tell you what's going on. I think it was Evil's last night. He's not here today, but last night he said something in chat about using the accelerometer recorder on your phone. There's some really cool apps out there that let you use the accelerometers in your phone. I have one. I don't remember the name, so I'm not gonna go look it up right now. And you could use those to put your phone on a surface that's vibrating, and it will give you a spectral analysis, or use the microphone on your phone and record some sound, and it will give you a spectral analysis. And if you look at the picture that's on your screen, the one in the thumbnail, that is a spectrum analyzer. So what that is it listens to a signal, and it in this particular case, let's see if we could zoom in on it a little bit. In this particular case, it was set up from 0 hertz to 5 kilohertz, and you can see there's a little spiky thing right around 1500 hertz, and it turned out that I was just measuring the vibrations in the equipment itself from fans and stuff, and there was a peak in that signal right there. And whoops, go back here. There we go. Let's see. Somebody just checked in. Lewis says hi from Glasgow, Scotland. 18 degrees science, 84% humidity, and just a bit cloudy. Welcome aboard, sir. Nice to see you. Carl says, are there FFT apps for phones? Yeah, absolutely. So you're going to make me look up the name of this app. I'll have to get it for you. But yeah, it will take a microphone input and it will turn it into a spectrum analysis, and that is an FFT. FFT stands for fast Fourier transform. And it's the thing that will take a time-based signal and turn it into a frequency-based signal. And that's what a spectrum analyzer does. Hey, Robin, welcome aboard. Stability lobe diagrams. So when I was studying feedback loops in college, there was a chart called the Nichols chart. And we had a nickname for it. But basically it was a stability chart, and you would plot where your stuff was living, and if you were close to this hole, you were in trouble. And the idea was to stay away from that hole. So yeah, these are things that you could also explore with a little hammer. So, it doesn't hurt to go over to, you got a tool in the lathe. You can go and tap it and listen for any vibrations. Frequently you won't hear anything, but sometimes if you hear a vibration, you might have a problem. One of the things Robin did when he built his solid tool post for the hard-inch lathe was specifically to remove a bunch of movement and make it stiffer, to take all of those resonant frequencies and shove them higher in frequency so that the work doesn't excite stuff and leave patterns, in part. Bodhi plot. So Carl says Bodhi plot, question mark. So a Bodhi plot is something else. It's a Bodhi plot gives you the amplitude on one graph and it gives you the phase on another graph. And as long as you don't approach the 180 degree phase shift at the same time you have greater than a gain of 1, then you can remain stable. But if you hit that magic spot on the Bodhi plot, which is similar to the Nichols chart, you start losing stability. And in the world of feedback systems, we have two terms. One is called phase margin, phase margin and gain margin. So if you hit the magic 180 degree phase flip, but your gain is way down, you're not going to go unstable. Similarly, if you hit the magic gain of 1 point and your phase is nowhere near 180, you're going to remain stable. So these are the things we look at. But this refers to feedback systems, right? And you can make the argument that your lathe, your grinding wheel, your tool, and in the mill, you can make the argument that they're feedback systems, but that gets really complicated to draw it out. So that's why chatter is that's non-randomness. It's little resonance bombs in your system. And Robin, you could probably speak to this a little bit. Precision Instrument put up a very short video within the last couple of days on one of their air bearings. And I hear a lot of good things about their air bearings, by the way. And they showed a 50-pound weight going on one of their air bearings, and then spin it with your finger, and it's just lovely. And then they take the same 50-pound weight and they put it on the air bearing of the other guys. I don't know who the other guys were, by the way, but it was the other guys. And they put it on there and they just touch it, and all of a sudden you hear the thing start howling. And there is an instability in that air bearing system above a certain weight. And it was fascinating. It was like, yeah, they're perfect. There's a resonance in that system. And it was not exceeding the ability of that air bearing per its specifications. It was within specifications. And it took off and started howling, vibrating. And that was really fascinating. So if you haven't seen that, go look it up on their YouTube channel. I swear it's a 2-minute video, but that was a really good example. We have different names for these things, chatter and whatever. Go check it out. But that was a perfect example. So when you design any of these things, or you're setting up a machine, you not only think about, do I have enough power? Is my tool going to take the cut? But also you have to think about dynamics and the impact of the dynamics, and is it going to start singing? And these are issues. Anybody here ever lose a wheel weight on their car, on one of their car wheels? It's the same exact thing. What's the first thing you do if your wheel starts bouncing up and down on the highway? You slow down. Or if you're Wes, you speed up. But that's one of those examples of, no, you should actually slow down. So there are tools for looking at these vibrations and knowing. Carl says air bearings can be musical instruments. I'm fascinated by that because it is a pretty simple system, but you have air, which is compressible, right? So that's a spring. You have a mass. It's the formula for resonance. No, your input is always welcome, Robin, and I want to hear it. So you want to come on audio? Yeah, here we go. push the button. Somewhere in Pennsylvania. Hello, you're on the air.
One of the things that I'm mildly familiar with is that in this whole realm of stability, there are a system where you have a calibrated impulse hammer of a given mass, and it has an accelerometer in it. And then you have other accelerometers that you put on the machine in various orientations, depending on what you're trying to do. And you smack your machine depending on what you're trying to do. And there's some finesse in that in getting the right amount of impulse that's in the right realm. But by doing that, you can identify the responses on those accelerometers will show the resonant frequency of whatever part you're attached to. And also, you can get a direct measurement of machine stiffness. So in rotary dresser spindles that I've designed, you would take the spindle and you can actually get the static stiffness axially and radially simply with an impulse hammer to determine how stiff the bearing system is. Because what you're seeing is you said this much force. You know how much force because you have the weight of the hammer is a known mass, and the accelerometer is telling you how fast it's hitting and the response of that. That gives you a known input force that basically calibrates the response of all the other accelerometers. It puts them all in scale to each other. And there's a friend of mine who works in the same industry who's probably one of the most knowledgeable. He's probably one of the most knowledgeable grind doctors. You see grind doctor in like cutting tool engineering.
Yep.
He's in kindergarten compared to this guy. He he worked with a guy that was a main machine tool engineer for one of the major companies and was just a master at this. And he learned from him and basically took over. So you get a situation where you've installed this rotary dresser system on a big machine, and they're telling you it's crap, right? You're the thing you just put on is a piece of junk, and he comes in and will show what's going on, and can even with knowing what's going on, he can say, well, all we have to do is put a mass of this much weight over here, and this will get rid of all of it. Okay.
Mm-hmm.
And because the machine is flimsy in a direction that is not the best, or
Right.
you might say, well, where you mounted it's no good because that's the weakest part of the machine and things of that nature. So
Right.
um, that and then the other thing that people have probably seen is when you have a machine tool, you can do that right at the cutting tool. And that's where you get those stability load diagrams. And they can actually show you for X number of flute tool at this RPM, because that's an excitation frequency because of the RPM and the number of flutes is basically hammering on the spindle that
Mm-hmm.
many times per revolution, helical or not, flutes.
Right.
Uh, and that based in the machine that can all give you its stability, and you can actually go and look and see where all these spots are, and it's it just goes like a staircase of various frequencies RPMs that you could run without even testing, I mean, without even running the parts and get that information. So
Yeah.
that's basically what I had was.
Yeah. If you had that kind of a software tool that can do the calculations, it could probably avoid some of the problems. But for the small guy, and I'm sure you could, correct me if I'm wrong, but for the small guy, and if you hear the thing, you could reach over and just change the speed a little bit and avoid the resonance. Of course, you've already made a mark on your work, but now you bring up an interesting point, which is in a mill, you're going to have a number of flutes, which is an input to the equation, but you're also going to have you mentioned a helical versus straight flutes. The stiffness of the tool is going to change based on whether it's helical flutes or straight flutes, and that
Yeah,
stiffness is
and
is
the
one of the
yeah.
springs, right?
Yeah, and the mounting system, is it HSK? Is it hydraulic? Is it, collet? Is it shrink fit? All those things all come into play in the actual effective stiffness because all those joints are all damping, somewhat damping mechanisms in the whole path there.
Yep.
And there are some machines I see that they're doing where they're actually working on dynamic analysis of this in the machine, so that the machine inherently knows where the stability lobes are for that particular in live, real time,
Right.
and adjust accordingly.
I like that. I like that a lot. And I wonder if that maybe James should look at possibly doing something like that. If you had an accelerometer on the system to provide the controller that kind of feedback, and the controller says, "Hey, wait a minute, you just started singing. I'm going to do something about it." That could be a nice feature in the control. Which this Haas feature is not. The Haas feature is just I'm gonna sweep around and avoid staying in any one place. But what I'm talking about is
That's
actual feedback.
that's somewhat of a different situation,
Hmm.
because once you start a chatter on like, let's just say we're lathe turning.
Right,
Once you start a chatter, it's regenerative.
right,
It's that was the chatter's already at the excitation frequency, the resonance of the system,
right.
and then it comes around again and it's getting excited at that. So by dialing up and down, you keep changing the chatter frequency, such that if you're clever with your over speed override dial, you can get out of situations. My son's really good at it on the lathe, because
Ooh,
you have things where
yeah.
this is not going to behave well, but we can get through this part just by cycling up and down, up and down, up and down, and you can't do it too fast, you can't do it too slow. You have to do it just right where it overlaps and kind of masks it, and you can do a manual version of that that's pretty helpful at times.
So so he's just like the Haas feature, the SSV feature, except you have to feed him.
Yeah.
Yeah.
And as a manual machinist, I give you some this would be things that people would know. But as a manual machinist, you can have situations where you say, okay, it's chattering, but I'm going to get within about 3 thousandths from the bottom of the groove. And then I'm going to shut the lathe off and I'm going to grab the chuck by hand and turn
Yes.
it by hand, because the frequency is so low, because your RPM is like zip, that you can go in there and peel off all that chatter and manually turn the chuck and peel those situations when you have, large tool engagement. And
I think we've seen Adam do that on one of his videos to get past some
yeah,
horrible chatter problem that was
you can
going
also
on.
do it by letting, when you got a big machine, you got quite a bit of inertia. You can just turn the lathe off and let the part inertia, as it slows down,
Yeah.
you go in and take those final cuts as it's coasting down and get the same effect, constantly changing speed. And
Yeah, that's like sweeping the input frequency down.
yeah, yeah,
That's pretty brilliant. Well, thank you, sir. Thank you for the input.
yep.
It was
Welcome.
exactly the kind of random we needed.
Okay.
Thank you, Robin. So, a lot of good ideas. I remember leaping for the spindle override switch on the Fanuc control several times, and that can save you. Let's see. So, anytime you have a spring and a mass, you have a resonance. Okay. So, in a mechanical system, air is compressible. That could be a spring, and then the mass is the weight of a thing. Anytime you have that, you can end up with a resonance. And what is one other thing? Let's see if anybody gets it. What is another thing you can do to a resonance to prevent it from being a problem, or to prevent its resonance from being stronger than the background noise? Anybody know? There's one element in the three required elements of a resonance that we haven't talked about. Thank you, Josh. Exactly correct. Damping. Okay. So damping is just loss of energy per cycle, right? So if you have a thing that's vibrating, and I mean, let's just do a thought experiment, right? We're going to go to Home Depot. We're going to get a wooden yardstick. Okay. We're going to take it home. We're going to stick the flat horizontal to the ground and hold it in our bench vise. We're going to take a hockey puck and we're going to tape it to the end of our wooden yardstick. Now, if we walk over to it and we pull the hockey puck down and we let go, what happens? It's going to vibrate. Okay. And if you stood there and you actually counted the oscillations that it went up and down until it finally stopped, you would have a number which is indicative of how resonant it is. Okay. And in some circles, we call that the Q. There's probably some other names for it. That's what I would call it. I would call it the Q. Now you walk over to the same system, and we're going to take a manila file folder, and we're going to tape that on top of the hockey puck. So we haven't appreciably changed the mass, but now it has a lot of drag in the air. And now we go ahead and we do the exact same thing. We're going to pull down on our yardstick with our hockey puck and our manila file folder, and we're going to let go, and it's going to start vibrating. But the drag of the manila file folder causes loss. It is dissipating energy as air movement, as turbulence. And now, if you counted how many times that system goes up and down, it may be like literally once. And that is called damping. So there are ways to damp chatter and make it go away, make the resonance go away. Now, I have seen, and I've talked to Dale about this, and we got some experiments we want to do, and I'll be talking to Robin also because I wanted to get his input. But I've seen people using magnets on the back of boring bars. So a boring bar is a perfect example on a lathe of a very long diving board, okay? And then, of course, you're cutting at the end of it. And sometimes, more often than many cutting situations, you will get that thing to start singing, okay? And I've seen people put magnets on the back of the boring bar, and it terminates the chatter. My question is, and I'm getting various contradictory reports on this. It's very controversial in my mind. Are you adding mass to the boring bar and thus changing the resonance system? Question number one. Question number two, are you establishing a magnetic path through the tool back into the machine and around back to the tool, which in itself provides what we call magnetic damping? I'm not sure. The answer is I'm not sure, but this needs to be investigated because it is effective. The other thing you see in boring, and if you want to talk about boring, it came to the right podcast, is inside the boring bar, you could have a rod and surrounded by a tube, which is the actual thing you see when you're holding the boring bar, and then fill it with grease or oil, and that provides damping. And that's very effective, and they don't give them away. Another thing that you see in those boring bars is literally valves that you can tune for a particular cutting situation, and it's literally amazing. I've seen 20-to-1, easily 20-to-1 boring bars cutting with absolutely not a hint of chatter using these techniques. That is all under the heading of damping. So now something was said recently which was incorrect, and I could say that with reckless abandon because I can't remember which video. It was a video, I believe. There we go. Thank you, Dale. Dale put a picture of the internally damped boring bar on the screen. Somebody said that if you put enough damping in, that it will reach, it will reach the final value and it won't overshoot, and then it will be critically damped. This was incorrect. So critical damping is slightly different. It's a very well-defined term, and what it is you'll have something that'll overshoot, and then it will settle down to the final value. That's called critical damping. If you have something that never overshoots and it reaches the final value, by definition, that is already overdamped. It's not evil and horrible and terrible. It's just the fastest way to get to the final value is critical damping, and it involves one overshoot. Okay? So if you could picture that, you approach a value, you overshoot it, and then it comes down and it settles onto the value. That's called critical damping. I'm being pedantic, but might as well get it right. And I'll get you some references. We'll find some references, and I'll put them in the notes. There's a book behind me somewhere. I think I could see it. Yeah, I think it's right. If you're watching the video, it's right there. That book right there. I'll find the details. So randomness can be used to avoid a resonance. Damping can be used to eliminate a resonance. And of course, stiffness in a machine or a grinding wheel or a tool, and in milling tools, we go to carbide. That's by definition is making it stiffer. Stiffness in the system pushes resonances to the right. It pushes them to much higher frequencies, so we don't excite them. So those are all different things, and they're all things that are useful to have tricks. I've seen a lot of getting back to chatter. I've seen a lot of tricks posted to Instagram where people are wrapping a big rubber thing onto the lathe work and putting a strap clamp on it. What is that doing? It's sort of doing two things at once, but the rubber part of it is adding damping. The mass part of it is changing the frequency of the resonance. And those are all good things. And sometimes you'll see people take rubber hose and stick it into the inside of a tube, which they're turning on the lathe, again, to get rid of the resonance. And that's predominantly damping from the rubber. So you could change the mass, you could change the damping, you could move the resonance. Those are the things you can do. But I like the idea of using randomness, using noise to avoid exciting the resonance. So Dale says rubber hose filled with lead shot / balls works really well. I changed that for you. Uh-oh. Robin has more to say. Let's see. Somewhere in Pennsylvania. Hello, you're on the air.
One of the things that should be mentioned that is like first grade machining.
Yes, sir.
But having your boring bar with the tool height high enough that at maximum downward deflection from your cutting forces, you do not exceed zero height, center height, because that is a self-generating situation. If you get right on center height, instantly the bar, as soon as it deflects at all, the depth of cut's increasing, and inherently, if you get in that zone there, I'm not sure whether the no chat bars will overcome that completely, but that's like first grade of boring, and sometimes it has to be pretty high. You have a long extension, you might say, oh my God, that bar is hanging down 30 thousandths when I take this big cut. Well, yeah, you better be 30 thousandths above center height when you dive in there. Second is when you're talking about the parts. Another technique which I just used with my son was doing some tubular parts in the Tormach,
Mm-hmm.
and procedurally we were doing them where they were starting out as solid, and they end up like 2 inch diameter solid. They only end up being an 1/8 inch wall thickness for about maybe 1 3/4 inches. So we had to rough out the insides close to that so that when we turned the outside didn't go to crap as far as roundness from internal stresses. So, but when we went to do that finish cut, after we're down to that almost that 1/8 inch wall, the first like 1/2 inch would have howl marks in it from basically it's a bell.
Mm-hmm.
So I turned a Delrin plug with just a few thousandths taper on it and stuck it in the hole. It was there. And all that did was change the entire resonant frequency of that bell so that that went away completely. So sometimes a rigid piece can do the same thing. Basically, I plugged the hole,
Yeah.
and since the
You're
bit
preventing it
was
from.
adjustable with it, kept just preventing it from doing that, and then pull it out when you're done and do the next one and on and on.
So the whole point about and Josh, I could see Josh had his eyes open up. He says that's why. Oh, that's why you put your boring bar above center line. So that's a very interesting point. And we would everything I've talked about so far has been in a linear system, but losing contact, right, when you stop cutting, that is a nonlinearity. That's a break in the curve, and absolutely that I could see that causing chatter, but that's not a linear function. That's a non-linear thing. It's like, oh, I've lost contact, or I'm starting to drag on the back of the tool now. I
If
didn't.
you read some of the information on the damped boring bars, you'll notice that they're very particular about how you're holding them.
Mm-hmm.
So if you put it in there and you're using 4 set screws on one side of it, they're going to say, no, that's not good enough. No, you're voiding the warranty. You have to have a full circle pinch engagement at least to go, or have like a HSK or a what's the triangular guys called? Um,
Dale's for
that's
every
pretty good.
Dale
Yeah.
says set screw will get you shot. Got it,
Yeah.
Dale.
So that's a big part of those systems
Mm.
also, and including the tool post and everything else that's involved.
Interesting. Have you ever had chatter since you went to your solid tool post on your cartridge?
Oh, sure. You still have the parts, the variable part of the system. You're not chattering because the tool post or the harding, because the harding is actually a beast of rigidity for the size of machine. Um, but no, you can still have chatter, but at least
Mm.
getting rid of all that. I tell you, running a machine with a solid tool post. I know I'm preaching to the choir probably, but that is just so ridiculously better than having a compound on.
Mm.
As far as tool library and all those things, it's just yeah, really good.
All right, I got to go get a hard inch now. All right, thank you, sir.
Yep.
All right, excellent. We're coming up to the top of the hour. If you guys have any questions on the topic, I hope we got some good ideas out there. But let me hit some other topics while we're here. Let's see. So a bit of a report from my shop, PFG Stones, out the door. All orders have been filled. There was some folks were waiting for 6-inch stones. They're all back in stock. We're getting thin on balancing stands, and we're getting thin on balancing rings. So I'm spooling that up for the next couple of weeks. We'll see if we can't get those back in stock. That's basically it. Everything else we're pretty healthy on in the PFG land. I don't have any other important notes for you in terms of the PFG output. If you guys need anything flat, need some stones, head on over to PFG.Stones.com and we'll take care of you. Yeah, so Carl says when the boring bar vibrates, the magnet slides and loses energy. So we have a real experiment ahead of us, because I am not convinced we actually know which of these effects have been demonstrated with the old magnet trick. And the old magnet trick absolutely works. I've seen enough videos where people are using it and there's no funny business going on, and it works. So the question is, which of the effects is the dominant effect? And I don't know the answer. So when we have a little time, we're going to set up some experiments and do this. And Dale's done it too. Yes. So Dale says another form of chatter is when drilling some material with long drills, you get the torque and the release screaming. So once again, look for the spring. Where's the spring? The spring is literally the drill twisting. And then at the bottom, you have the cutting edge. And then finally, the cutting edge makes its cut. So you have your drill is the spring. And that's a form of chatter. Absolutely. If you were suddenly able to make that drill stiffer, Dale, torsionally stiffer, then you would control that. If you went to carbide instead of, well, let me ask you the question: in your experience, is it carbide or high-speed steel? Inquiring minds need to know. All of them, yeah, yeah. So if you had that happening with a high-speed steel drill, and you didn't change any parameters, and you went to a carbide drill, my guess is it's betterer. It's more gooder, as we say, right? You taught me the correct way to say that. It's more gooder. So we have a couple of things in the pipeline. I'm working on. It's the goodest material. It is. Make it out of unobtainium. We have some expertise coming. I'm hoping to get them locked down for sometime in the next couple of weeks, for a company that makes thread locking compounds. That actually will be very interesting. And there's some other stuff coming. There's a big internet event happening in the next couple of months that we're going to get one of the representatives to come talk to us about. I know I'm being very uninformative, but that's what I'm good at. So that's in the pipeline, and we'll see what happens. In the meantime, if there's anything we could do for you, let us know. Get flat, stay flat, and remain random. And we'll see you probably next week. Take care.